When we contemplate time travel, we're not merely engaging in a fantastical thought experiment. We're in fact asking one of the most profound questions that the universe permits us to articulate. Can the relentless second-by-second march we all experience be anything but absolute? Can we navigate time as we do space, moving forward, backward, or even sideways? It's a question that resonates deep within our scientific and philosophical foundations, for the very laws of physics as we currently understand them do not explicitly forbid such journeys. They don't cast an outright veto upon the notion. Instead, they present us with something far more intriguing, a tapestry, woven with extraordinary paradoxes, logical knots that seem almost impossible to untangle, threads of causality that twist back upon themselves in defiance of our everyday intuition. To truly grasp this, let me introduce you to something that might at first seem counterintuitive. Einstein's monumental theory of general relativity, published in the cosmic year of 1915, actually permits certain astonishing solutions. Geometries of space-time so warped and intricate that they sculpt what we term closed time-like curves. These are not mere theoretical constructs. They are pathways, possibilities, etched within the very fabric of existence, allowing a journey that loops back upon itself, a return to an earlier moment in one's own timeline. Einstein himself, a man whose mind stretched the boundaries of reality, was deeply troubled by these implications. He found the mathematical elegance unsettling, the consequences of such curves profoundly disturbing. Yet the beautiful, unyielding mathematics of curved space-time cares little for human comfort or discomfort. It simply describes what could be. The first to truly gaze into this abyss of temporal possibility was Kurt Gödel, the brilliant mathematician celebrated for his incompleteness theorems. In 1949, Gödel, as a birthday gift to Einstein, unveiled an exact solution to Einstein's field equations. It described a rotating universe, and within this Gödel universe, closed time-like curves existed everywhere. You could theoretically journey into your own past. Einstein, though, disturbed, could find no mathematical error. The solution was, to his consternation, valid. This brings us to the very heart of the conundrum, the paradoxes. The most infamous, of course, is the grandfather paradox. Its chilling simplicity has echoed through countless scientific and philosophical debates. Imagine constructing a time machine and journeying back to a time before your parents were even conceived. You encounter your grandfather as a young man, and for reasons perhaps known only to your future self, you prevent him from meeting your grandmother. Maybe an accident, a subtle misdirection, or a more direct intervention causes his demise. What then, if your grandparents never meet your parent is never born, and by extension, you are never born? But if you are never born, you cannot have travelled back in time to prevent their meeting in the first place. Therefore they do meet, you are born, you do travel back. And so the cycle relentlessly spins, an impossible Ouroboros of cause and effect. It is a logical impossibility, a paradox in the truest sense, a self-defeating loop that threatens to unravel the very coherence of reality. For decades, physicists have wrestled with this, seeking resolutions that reconcile the mathematical possibility of closed time-like curves with the logical impossibility of such paradoxes. Some of the proposed solutions are in their own right as extraordinary as the idea of time travel itself. One elegant approach posits that the universe simply will not allow paradoxes to materialize. This is known as the Novikov self-consistency principle, named after the Russian physicist Igor Novikov. The core idea is that if you attempt to create a paradox, the laws of physics will subtly conspire, orchestrating events to prevent any inconsistency. So if you journey back in time with the intent to kill your grandfather, you will find through a cascade of improbable but utterly consistent events that you simply cannot. Perhaps your weapon jams, or you slip on an unforeseen patch of ice, or a sudden inexplicable change of heart overtakes you at the crucial moment. Whatever the specific mechanism, the timeline remains inviolate, seamlessly consistent. There's even a beautiful, albeit miniature, experiment that probes a version of this principle, not with grand temporal journeys, but with the elusive dance of photons and quantum mechanics. It's been dubbed the Quantum Grandfather Paradox Experiment, meticulously carried out by researchers at the University of Queensland in Australia. They simulated a photon travelling back in time through a hypothetical wormhole and interacting with its own past self. The results were nothing short of fascinating. The intrinsic probabilities of quantum mechanics automatically adjusted themselves, preventing any paradox from emerging. The photon could not destroy its past self in a way that would negate its future existence. Nature, it seems, intrinsically safeguards its own logical coherence, even at the most fundamental scales. Yet another solution to the paradox, one that bends the mind even further, emerges from the very fabric of quantum reality, the many worlds interpretation applied to time travel. This radical perspective suggests that when you journey back in time and instigate a change, you don't actually alter your own past. Instead, your actions trigger a branching of reality, giving rise to a parallel universe, a new timeline where events unfold differently. So you travel back, prevent your grandparents from meeting, but this pivotal act occurs within a freshly formed branch of reality. In your original timeline, you were still born, you still built the time machine, you still embarked on your journey. But now, another universe exists distinct and equally real where you were never born. Both realities persist, both are valid expressions of cosmic possibility. This profound concept stems from the work of pioneering physicists like Hugh Everett III, who first proposed the many worlds interpretation in his Princeton doctoral dissertation in 1957. Everett suggested that every quantum measurement, every probabilistic outcome causes the universe to split into multiple branches, each embodying a different possible result. When extended to time travel, this implies that every temporal journey, every interaction with a past moment perpetually creates new branches, new histories. You cannot rewrite your past, but you can endlessly generate alternative pasts. David Deutsch, a distinguished physicist at Oxford, has extensively developed this idea, demonstrating that when the many worlds interpretation is combined with the rigorous laws of quantum mechanics, time travel becomes theoretically possible without ever encountering a paradox. You could indeed journey to the past, you could interact with it, but your actions would invariably forge new timelines, rather than retroactively altering your own. Mathematically, it presents a perfectly consistent picture. Whether nature in its boundless complexity actually operates in such a spectacular, ever-branching manner remains one of the most compelling open questions in physics. Now let us turn our gaze to the audacious question of how one might actually construct such a temporal conveyance, because this is where the theoretical physics truly begins to ignite the imagination. Several theoretical proposals exist, and they all converge on a singular monumental requirement: the extreme bending and twisting of space-time itself. The most celebrated of these conceptual gateways is undoubtedly the wormhole often referred to as an Einstein-Rosen bridge. Though first described in a 1935 paper by Einstein and his colleague Nathan Rosen, they did not initially conceive of it as a vehicle for temporal journeys. A wormhole is in essence a tunnel through the vast expanse of space-time, an exotic shortcut connecting two distant points. Imagine space-time as a flat sheet. Now fold that sheet so that two widely separated points physically touch. A wormhole represents the ephemeral connection between those points, allowing instantaneous passage. If one could somehow create or stumble upon such a cosmic anomaly, instantaneous travel to distant locations would be within reach. But here is the critical juncture where it transforms into a time machine. If one end of this wormhole is accelerated to near the speed of light, profound time dilation occurs. Time for the moving end would pass significantly slower. Upon its return, the two mouths of the wormhole would no longer be synchronized in time. Enter one end and you would emerge from the other, not merely at a distant location, but at an earlier point in time. Kip Thorne, the eminent physicist and Nobel laureate whose work illuminated the mysteries of gravitational waves, has delved deeply into this intricate dance of space-time. In the 1980s, he was famously approached by Carl Sagan, then crafting his novel Contact, who sought a scientifically plausible means for his characters to traverse immense cosmic distances. Thorne's suggestion of wormholes spurred his own serious inquiry into their properties. He and his collaborators subsequently published papers demonstrating that while wormholes are indeed permitted by general relativity, maintaining them in an open, traversable state would necessitate something truly extraordinary, exotic matter material possessing negative energy density. Such matter has never been observed in nature, at least not in any macroscopic stable form. However, the esoteric realm of quantum mechanics offers tantalizing hints that it might exist in minute quantities under specific conditions, as evidenced by phenomena like the Casimir effect. Consider the Casimir effect, a beautiful, delicate quantum phenomenon unearthed by the Dutch physicist Hendrik Casimir in 1948. It is a whisper from the void, an experimental testament to the universe's strange allowances. Imagine two uncharged, perfectly parallel metal plates positioned infinitesimally close within a vacuum. Here, the tumultuous quantum fluctuations of the electromagnetic field, the very effervescence of empty space, are subtly altered. The energy density between the plates becomes negative relative to the surrounding vacuum, generating a minute yet measurable attractive force that pushes the plates together. This tiny gravitational caress demonstrates that negative energy density is not merely a theoretical abstraction. It is a demonstrable aspect of reality. Yet scaling this effect up to generate the colossal amounts of negative energy required to keep a wormhole mouth open and stable, it remains a monumental challenge, a leap beyond our current technological capabilities by many, many orders of magnitude. It is akin to using the delicate flutter of a butterfly's wing to power a starship. Beyond wormholes, other theoretical pathways to temporal manipulation have been proposed. One involves the mind-bending complexities of rotating black holes known as Kerr black holes, after the mathematician Roy Kerr, who elucidated their solution in 1963. When a black hole spins, it profoundly drags space-time around it, a phenomenon called frame dragging. Within the abyssal interior of such a rotating black hole, the structure of space-time becomes incredibly intricate. It is theorized that there might exist paths routes through this cosmic maelstrom that could allow one to bypass the singularity at the core and potentially emerge in a different time or even a different universe. However, the journey itself would subject any unfortunate traveller to tidal forces so extreme, so immense, that the very fabric of their being would be torn apart long before any temporal displacement could be experienced. We gruesomely term this spaghettification. Another ingenious, though equally impractical idea emerged from Frank Tipler, a mathematical physicist, in 1974, the Tipler cylinder. This involves an infinitely long cylinder composed of incredibly dense matter, rotating at an incomprehensibly rapid speed. The elegant mathematics reveals that if one were to navigate around this colossal cylinder in a very specific helical path, a journey into one's own past could in principle be achieved. The glaring problem, of course, lies in the prerequisites infinite length and matter so unimaginably dense that its creation is utterly beyond any conceivable technology. It remains a fascinating mathematical curiosity far removed from any practical blueprint. Then there is the Alcubierre drive proposed by the Mexican physicist Miguel Alcubierre in 1994. This concept, while not a time machine in the traditional sense, is intimately related to the manipulation of space-time. The idea is to contract space-time in front of a spacecraft and expand it behind the craft, creating a warp bubble of curved space-time that carries the ship along. Crucially, the vessel itself remains within a flat, unaccelerated region of space-time inside this bubble, thus circumventing the relativistic speed limit within its local frame. By manipulating space-time itself rather than moving through it, one could potentially travel effectively faster than light without violating the principles of relativity. And if you can travel faster than light, you can in principle arrive at a distant destination before light from your departure point reaches it, implying a form of backward motion in time relative to that destination. Like the traversable wormhole, the Alcubierre drive also demands exotic matter with negative energy density, and the quantities required are astronomical. Early calculations suggested the need for more negative energy than exists in the entire observable universe. Subsequent refinements have somewhat reduced this colossal requirement, but it remains vastly beyond anything we can currently produce. Still, the beauty and terror of it all is that it is not fundamentally forbidden by the known laws of physics. It is merely for now really, really hard. What resonates deeply within all these theoretical proposals, from the wormholes to the warp drives, is a common thread. They are without exception permitted by the current framework of physics, but they demand conditions or materials that are either unattainable with present technology or simply unobserved in the natural universe. It is as if nature in its infinite wisdom is whispering, yes, time travel is possible, but I shall make it extraordinarily difficult for you to achieve. Is there some deeper overarching principle at play, some cosmic censorship that actively prevents paradoxes from ever manifesting? Stephen Hawking, with his characteristic brilliance, pondered this very question. He proposed the chronology protection conjecture, suggesting that the laws of physics inherently prevent the formation of closed time-like curves, except perhaps on microscopic fleeting scales. However, he could never definitively prove it. It remains a conjecture, a tantalizing hypothesis awaiting the definitive judgment of a complete theory of quantum gravity. Indeed, it is in the elusive realm of quantum gravity where the true answers likely reside. General relativity, while a masterwork, allows for time travel under certain extreme conditions, but it does not account for the probabilistic, granular nature of quantum mechanics. And quantum mechanics, in turn, harbours its own peculiar relationship with time. At the quantum level, particles exist not in definite states, but in superpositions in multiple states simultaneously, until the act of measurement collapses their wave function. Time itself in the quantum mechanical framework is often treated as an absolute unyielding parameter, a steady background clock, not something that can be warped or twisted like the fabric of space-time. When we eventually achieve a unified theory, one that seamlessly weds general relativity with quantum mechanics, be it string theory, loop quantum gravity, or some yet unimagined framework, it will, we hope, definitively pronounce upon the possibility of time travel. It might declare that closed time-like curves are mere mathematical artifacts, beautiful, but ultimately unreal, forbidden in the true universe. Or it might affirm their existence, but only under conditions so extreme, so alien, perhaps deep within the heart of black holes, or at the very incandescent moment of the Big Bang, that they will forever remain beyond our reach. Beyond the mechanics, there's another profound aspect to consider: causality. Our entire perception and understanding of the universe, from the simplest physical interaction to the most complex human narrative, is built upon the foundational premise that cause precedes effect. A glass is dropped, it falls, it shatters. The act of dropping is the cause, the shattering the effect, not the other way around. But with the introduction of time travel, this sacred sequence becomes bewilderingly confused. An effect could precede its cause, or even more unsettling, it could cause itself. A truly wonderful thought experiment known as the bootstrap paradox, or ontological paradox, vividly illustrates this disquieting possibility. Imagine you journey back in time, not with malicious intent, but with a gift, a complete bound collection of William Shakespeare's plays. You present this anthology to the young Shakespeare. He in turn publishes them under his own name, and they become the timeless classics we revere today. Centuries later, you, a devotee of literature, discover this very collection, are moved by its genius, and decide to embark on a temporal journey to deliver it to Shakespeare in the past. The profound question then arises: who ultimately authored these plays? You did not. You merely copied them. Shakespeare did not. He received them from you. The information, the very essence of the plays, exists in a closed causal loop with no apparent original creator. It bootstrapped itself into existence, a self-generating enigma. The bootstrap paradox unveils something profoundly unsettling about information and causality. Where does information originate if it has no origin point? In our everyday experience, every piece of information, every novel idea, every artistic creation has a source and inventor. A composer writes a symphony. A mathematician proves a theorem. A poet pens a verse. But in a closed, time-like curve, information could simply be existing without ever being initiated. And this deeply troubles us, for it violates our most fundamental intuition about how reality, how creation should function. There is a related, subtly different paradox known as the predestination paradox. In this scenario, your attempts to alter or preserve the past are precisely what create the future you are attempting to influence. A classic example: you travel back in time to avert a catastrophic disaster, only to find that your very presence, your very actions, inadvertently trigger the disaster you sought to prevent. You become an inseparable, indispensable part of the causal chain leading to the event you wish to negate. It is self-fulfilling rather than self-contradictory, making it curiously consistent with the Novikov principle. But it raises profoundly uncomfortable questions about free will. If you are destined to travel back and cause the event, did you ever truly possess a choice? Or was your decision merely a predetermined unfolding of events that had in a deeper sense already occurred? This plunges us into deep philosophical waters, touching upon the ancient debates of determinism versus free will and the very nature of human choice itself. Some physicists suggest that in a universe where closed time-like curves are a reality, free will, at least on a cosmic scale, might be an elaborate illusion, even if it feels exquisitely real to us in each passing moment. A fascinating area of contemporary research delves into the possibility of time travel, not with human voyagers or starships, but with the ephemeral dance of information and quantum particles. Quantum mechanics, in its glorious strangeness, allows for phenomena that seem to utterly defy our linear sense of time. Take quantum entanglement, for instance. When two particles become entangled, their fates are inextricably linked no matter how vast the distance separating them. A measurement performed on one instantly superluminally influences the state of the other. Einstein famously disturbed by this dubbed it spooky action at a distance, believing it violated the sacred speed of light limit. Yet countless experiments have rigorously confirmed its reality. Some interpretations of quantum mechanics even suggest a subtle form of retrocausality, where future events might in some enigmatic way influence past ones. This is dramatically explored in delayed choice experiments, first conceptualized by John Wheeler in the 1970s and 80s. In these ingenious setups, a decision made after a photon has already traversed an experimental apparatus seems to retroactively determine how it behaved before the choice was made. Variations of these experiments have been meticulously performed in laboratories across the globe, and their results consistently align with the predictions of quantum mechanics, even as they profoundly challenge our ingrained linear notions of cause and effect. Seth Lloyd, a physicist at MIT, has proposed using the very principles of quantum mechanics to resolve the gnarly issues of time travel paradoxes. His idea involves a combination of quantum teleportation and post-selection. Essentially, if you attempt to engineer a paradoxical outcome, the probability amplitude for that outcome would simply collapse to zero. The universe doesn't actively forbid your attempt. Rather, quantum mechanics inherently ensures that the attempt always fails in a way that preserves absolute consistency. It is an elegant solution, the same mathematical structure that gives rise to quantum superposition and entanglement automatically erects a natural barrier against paradoxes. Laboratory simulations utilizing optical systems and rudimentary quantum computers have been constructed by researchers at the University of Vienna and other institutions. These are not actual time travel experiments, of course, but they rigorously test the underlying mathematical framework. And consistently, they find that quantum mechanics resolves potential paradoxes automatically. The system always evolves in ways that prevent logical contradictions, a testament to nature's deep-seated integrity. Allow me to introduce you to another theoretical possibility, one that possesses a peculiar kind of beauty, the idea of time crystals. These are not crystals in the geological sense, but rather patterns that repeat in time instead of space. Just as an ordinary crystal exhibits a structure that repeats spatially atoms arranged in a precise repeating lattice, a time crystal possesses a structure that oscillates or repeats in time, maintaining a dynamic pattern indefinitely, without any external energy input. This seemingly defies the very tenets of thermodynamics. Yet in 2012, Nobel laureate Frank Wilczek proposed their theoretical existence. For years, physicists debated whether time crystals were truly possible. Then between 2016 and 2017, several independent groups triumphantly created them in laboratories utilizing chains of ions and other intricate quantum systems. They exist these strange, captivating states of matter that fundamentally break time translation symmetry. They do not grant us time travel directly, but they offer a profound glimpse into a universe where time is more flexible, more intricately structured than our everyday experience suggests. They hint at possibilities we have yet to fully explore. Now, I want to discuss something that might initially appear unrelated, but bear with me, for it is intimately connected: the arrow of time. Why does time flow relentlessly in one direction? Why do we possess vivid memories of the past but no knowledge of the future? Why do eggs shatter but never spontaneously reassemble themselves? This is one of the deepest, most enduring mysteries in all of physics, and it holds the key to our understanding of time travel. The fundamental laws of physics at their most microscopic level are almost entirely time-symmetric. If you were to film elementary particles interacting, and then play that film backward, you would generally be unable to tell the difference. The equations function perfectly well in either temporal direction. There is one minuscule exception involving certain rare particle decays, but its effect is far too minor to account for the powerful unidirectional arrow of time we experience macroscopically. So from whence does this arrow emerge? The answer, it seems, lies not in fundamental particle interactions, but in thermodynamics, specifically in the concept of entropy. The second law of thermodynamics declares that entropy, which can be broadly understood as disorder or the number of possible microscopic arrangements of a system, always increases in a closed system. A shattered egg possesses vastly higher entropy than an intact one, simply because there are an astronomically greater number of ways its molecules can be arranged in a broken state. The universe as a whole is inexorably moving from a state of lower entropy to higher entropy, and this increase, this relentless march toward disorder, is precisely what gives us our profound sensation of time's linear flow. But here's the truly mind-bending part: if one could somehow reverse the momentum of every single particle in the universe, the fundamental laws of physics dictate that everything would run backward. Entropy would decrease, shattered eggs would reassemble themselves with impossible grace, and time would appear to flow in reverse. It is only the highly specific initial conditions of the universe, the astonishing fact that it began in an exceptionally low entropy state at the Big Bang, that gives rise to the unidirectional arrow of time we so deeply experience. Time travel then might not simply be about navigating through space-time, but about somehow reversing or artfully circumventing this entropic arrow, a cosmic defiance of disorder. Some physicists, like Sean Carroll at Johns Hopkins, have explored the radical idea that the arrow of time might manifest differently in distinct regions of space-time. Perhaps within the event horizons of black holes, or in other universes within a vast multiverse, time could flow in alternative directions. If you were to journey to such a region, would you experience time literally running backward? Would the very sequence of cause and effect be inverted? It is deeply speculative, certainly, but it arises from the rigorous process of taking the laws of physics seriously and following their mathematical implications to their logical, albeit extreme, conclusions. There is also the profound question of whether the past and future even exist in the same way as our present moment. This delves into the ancient philosophical debate between presentism and eternalism. Presentism asserts that only the present moment is truly real. The past has ceased to exist and the future has not yet come into being. Eternalism, in stark contrast, proposes that all moments in time, past, present and future, are equally real, existing simultaneously in a four-dimensional space-time block, a static cosmic tapestry. Our perception of a now moving through time is, in this view, merely a feature of our consciousness, not a fundamental aspect of reality itself. If eternalism is the correct depiction, if the block universe is the true nature of reality, then in a curious sense, time travel becomes less paradoxical. Your past self already exists perfectly real out there in the vast landscape of space-time, just as real as your present self. Travelling to meet them isn't changing anything. It's simply navigating through the intricate landscape of space-time in an unusual, perhaps challenging manner. The timeline in this view already includes your arrival from the future. It always has. You cannot change it, for there is nothing to change. You are merely fulfilling what always was an integral part of the universe's preordained narrative. However, if presentism accurately describes reality, if only the ephemeral present moment truly exists, then time travel becomes infinitely more problematic. You would be journeying to a past that no longer exists, potentially creating it anew in the process, or leaping to a future that has not yet materialized, collapsing infinite possibilities into a single reality by your mere observation. The philosophical implications, regardless of which view is correct, are staggering. Julian Barber, a brilliant British physicist, has proposed an even more radical and deeply counterintuitive idea that time in any fundamental sense doesn't exist at all. In his view, what we perceive as time is an illusion, a construct created by the way our consciousness interprets a sequence of static configurations. Each moment is a separate now, and these moments do not inherently flow into one another. We perceive flow because our memories weave a narrative creating a continuity, but fundamentally there is no such thing as time passing. If Barber's hypothesis holds true, then the very concept of time travel becomes in a literal sense meaningless. You cannot travel through something that does not exist. However, paradoxes like the grandfather paradox would likewise dissolve, for they rely on a notion of temporal flow that in this framework is not real. These are deep philosophical waters indeed. I know we have traversed from the engineering problems of building a time machine to the most fundamental questions about the nature of reality itself. And this transition is entirely appropriate, for the very inquiry into time travel forces us to confront these profound questions head-on. It is not merely a science fiction fantasy. It is a powerful probe into the heart of physics and philosophy, a catalyst for re-evaluating our most basic assumptions about existence. What consistently strikes me about all these paradoxes and proposed solutions is their capacity to expose assumptions we didn't even realize we were making. We implicitly assume, for instance, that there exists a single objective, universally shared timeline. Yet the combined insights of quantum mechanics and relativity suggest that reality might be far more convoluted. Different observers, particularly those moving at relativistic speeds, can genuinely disagree about the order of events, about what constitutes simultaneity, and even about the precise duration between moments. And from their respective reference frames, each observer is entirely correct. This concept, known as the relativity of simultaneity, is central to Einstein's theories. If you are moving at a substantial fraction of the speed of light relative to me, events that I perceive as happening at precisely the same time will appear to occur at different times to you. There is no absolute now that spans the entirety of the universe. Your present moment and my present moment are distinct non-overlapping slices through the vast four-dimensional block of space-time. This might seem abstract until you grasp its profound implications for time travel. If there is no universal present, then the very act of travelling to the past becomes ambiguous. Whose past relative to which specific reference frame? This intertwines with something called the Reitdijk-Putnam argument, which suggests that the relativity of simultaneity inherently implies a block universe where all events past, present and future are equally real and fixed. If observers can genuinely disagree about simultaneity, then future events must already exist in some fundamental sense. Otherwise, logical contradictions would abound. It is a powerful philosophical argument rooted in physics, though not all philosophers or physicists universally accept it. Nevertheless, it is deeply thought-provoking, suggesting that our visceral experience of time as a flowing river with an open, malleable future might be fundamentally misleading. let me introduce you to the intriguing if elusive concept of tachyons, hypothetical particles that would travel faster than the speed of a light. They were first seriously proposed by physicists in the 1960s, notably Gerald Feinberg. The mathematics of relativity surprisingly does not explicitly forbid faster-than-light particles. It merely dictates that they would possess imaginary mass and exhibit profoundly strange properties. If tachyons genuinely exist, they would experience time in a manner fundamentally different from our own. From their perspective, they might effectively move backward in time, and if one could somehow send signals using tachyons, communication with one's own past would become possible. This immediately reignites the paradox problem. You could send a message to your past self stating, "Do not send this message," thereby creating an inescapable logical contradiction. Because of this inherent paradox potential, most physicists harbour a strong suspicion that tachyons do not exist. Despite rigorous searches, not a single one has ever been detected. It seems plausible that nature might forbid them precisely because they would permit such paradoxes. However, we cannot be entirely certain. There might exist some principle yet undiscovered that allows for faster-than-light particles while simultaneously safeguarding causality from paradoxes. String theory, that ambitious grand endeavour to unify all of physics, offers its own intriguing perspectives on the nature of time and causality. In this profound theoretical framework, the universe's fundamental constituents are not point-like particles, but rather infinitesimal vibrating strings of energy. These strings, which can be open or closed loops, vibrate in different modes, giving rise to the myriad particles we observe. The theory necessitates the existence of extra spatial dimensions beyond the 3 spatial dimensions and 1 temporal dimension we directly experience. These extra dimensions are hypothesized to be curled up, compactified to scales so infinitesimally small that we cannot directly detect them. Yet in certain versions of string theory, these hidden dimensions could exert a subtle but profound influence on causality. There might exist pathways through this higher dimensional space that effectively act as shortcuts through our familiar 4-dimensional space-time. Travelling along such a convoluted path could theoretically transport you to a point in your own past. The mathematics is incredibly complex, involving esoteric concepts like Calabi-Yau manifolds and D-branes. But the crucial takeaway is that string theory does not automatically prohibit closed time-like curves. Whether they can actually manifest in realistic, stable models of the universe remains a vigorous debate among string theorists. Loop quantum gravity. The other major contender in the quest for quantum gravity offers a distinctly different perspective on time. In this theory, space and time themselves are not continuous, but quantized granular, composed of discrete units akin to a pixelated image at the smallest possible scales. The Planck length, approximately 10 Dau 35 meters, and the Planck time, about 10 Dau 43 seconds, represent the fundamental grains of space-time. Below these scales, our usual macroscopic notions of space and time utterly break down. In loop quantum gravity, time might not be a fundamental feature of reality at all, but rather emerge from something more basic. Carlo Rovelli, one of the theory's founders, has written extensively on this. He suggests that time as we experience it is not fundamental, but arises from our specific perspective, from the way we interact with and coarse-grain information about the universe. At the true quantum gravity level, there might be no time at all, just a complex web of relationships between quantum states. If this radical view is correct, then the very concept of time travel paradoxes might simply dissolve, for they rely on a notion of time that only exists at macroscopic emergent scales. Now let's consider something more tangible, or at least more immediately comprehensible, the possibility of observing the past without physically journeying to it. In a limited sense, we do this constantly. Every time you gaze at a distant star, you're seeing it not as it is now, but as it was years or even centuries ago, because light, though incredibly fast, requires finite time to travel across the cosmic abyss. The majestic Andromeda Galaxy, our nearest galactic neighbour, appears to us as it was 2.5 million years ago. astronomers routinely peer into the deep past by observing faraway cosmic objects. But could we observe our own past here on Earth? If you possess the capability of faster-than-light travel, you could in principle outrun the light that left Earth long ago, and then turn around with a powerful telescope to witness historical events unfold. Imagine racing to a point several light years away, then aiming a formidable telescope back at our blue planet. You would be observing Earth's past, a living historical record unspooling before your eyes. Of course, this hinges on faster-than-light travel, which as we've discussed remains a profound challenge. Nevertheless, it's a powerful thought experiment, illuminating how the finite speed of light creates a kind of historical echo, continuously propagating outward through the vastness of space. There's another intriguing avenue through which information from the past might theoretically be recovered: the holographic principle. This profound principle, developed by physicists Gerard de Hooft and Leonard Susskind in the 1990s, proposes that all the information contained within a volume of space can be entirely encoded on the boundary of that space. It emerged from their deep studies of black holes and has since become a central, almost mystical concept in modern theoretical physics. If the holographic principle holds true, then information about all past events, every single quantum interaction, might be subtly encoded on distant boundaries of space-time. Recovering and decoding this information would demand technologies beyond anything we can currently conceive, but in principle, it might not be impossible. It suggests that the past is not truly gone, but merely projected a cosmic memory etched onto the universe's ultimate canvas. Black holes themselves present a vortex of fascinating questions about time and information. When an object falls into a black hole, crossing the point of no return known as the event horizon, from our external perspective, time for that object appears to slow down infinitely. We never actually see it cross the horizon. We perceive it as perpetually frozen just outside, growing progressively dimmer and redder. But from the perspective of the infalling object itself, time passes entirely normally. It crosses the event horizon in a finite subjective time. This is time dilation frame-dependent taken to an unimaginable extreme. Stephen Hawking famously demonstrated in the 1970s that black holes are not entirely black. They emit radiation due to peculiar quantum effects near the event horizon, and they eventually evaporate entirely. This led to the infamous black hole information paradox. If a black hole eventually evaporates, what then becomes of the intricate information about everything that fell in quantum mechanics staunchly maintains that information can never be truly destroyed, yet it seems to vanish into the black hole only to disappear into nothingness as the hole evaporates. Recent theoretical work suggests the information might be preserved in a scrambled form within the Hawking radiation, or perhaps subtly encoded on the event horizon itself, or even stored in a persistent remnant after evaporation. Some proposals even involve Einstein-Rosen bridges, tiny wormholes connecting the black hole's interior to another region of space-time, or even to an entirely different universe. These ideas blur the conventional boundaries between black holes and wormholes, between singularities and cosmic gateways, and all of them carry profound implications for time travel, especially given that rotating black holes, as previously mentioned, possess interiors where time becomes fantastically complicated and tangled. Let me momentarily diverge to discuss cosmic strings. These are hypothetical one-dimensional defects in space-time that may have formed during the universe's nascent moments, akin to infinitesimal cracks in a freezing cosmic fluid. They would be incredibly thin, perhaps no wider than a proton, yet would stretch across unimaginable distances, potentially spanning entire galaxies. And they would be extraordinarily dense, possessing a tremendous mass energy per unit length. In 1991, J. Richard Gott showed that if two such cosmic strings were to hurtle past each other at relativistic speeds, their gravitational fields could in principle create closed time-like curves in their vicinity. The intricate geometry would allow a traveller to loop around the strings and return to their starting point in both space and time, arriving before they left. This ingenious mechanism wouldn't require exotic matter or negative energy. only the immense mass energy of the cosmic strings themselves and their furious relative motion. The significant catch, of course, is that we have no definitive proof that cosmic strings even exist. They are predicted by some theories of the early universe, but have never been directly detected. Gravitational wave observatories and cosmic microwave background studies are diligently searching for their subtle signatures, but so far nothing conclusive has emerged. The early universe itself, the incandescent epoch immediately following the Big Bang, might have been a place where time functioned in fundamentally different ways. At the very moment of creation, or more accurately in the first fleeting instants after it, the universe was unfathomably hot, dense, and energetic. All four fundamental forces of nature might have been unified into a single supreme force. Space-time itself in this primordial crucible might have existed in a quantum superposition of different geometries. Some theories propose that time as we comprehend it simply did not exist before the Planck epoch, the first 10 to Wu of 43 seconds. Before that, or perhaps instead of that, there might have been an entirely different underlying structure. Models like the Hartley-Hawking no-boundary proposal suggest that the universe has no true beginning in time, because time itself becomes space-like as you approach what we conventionally label the Big Bang. Imagine the surface of a sphere. It has no edge, no boundary, even though the surface area is finite. Similarly, space-time might be finite in the past direction, but without a singular starting point. In such a model, asking what happened before the Big Bang becomes as meaningless as asking what is north of the North Pole. The question doesn't make sense because the direction you're asking about simply doesn't exist within that geometry. If time emerged from something else, if it wasn't always a fundamental feature of reality, then travelling backward in time might entail approaching a regime where time ceases to have meaning. You couldn't traverse further back than the point where time itself begins or emerges or crystallises out of quantum uncertainty. The ultimate barrier to time travel might not be the paradoxes or the insurmountable energy requirements, but the simple, profound fact that there's no there to travel to beyond a certain temporal horizon. I find it profoundly beautiful, almost poetic, how all these seemingly disparate ideas, time travel, paradoxes, quantum mechanics, the nature of information, black holes, holography, quantum gravity, and the fundamental structure of space-time interconnect. Each question, each revelation seamlessly opens onto deeper, stranger questions like a fractal pattern of inquiry, extending inward toward the very heart of reality itself. There's something I wish to explore now beyond the theoretical proposals and mathematical frameworks, the experimental side of things. Have we in our scientific endeavours actually tested anything truly related to time travel or time dilation? The resounding answer is yes, we have. Not time travel in the dramatic science fiction sense of sending a human into the past, but we have unequivocally confirmed that time is relative, that it can be stretched and compressed, that different observers genuinely experience time at different rates. The Hafele-Keating experiment in 1971 stands as one of the first direct audacious tests of this principle. Joseph Hafele and Richard Keating embarked on a global journey with atomic clocks' incredibly precise timepieces that measure time by counting the oscillations of cesium atoms. One set of clocks flew eastward, one westward, and a control set remained firmly on the ground at the US Naval Observatory. Upon their return, when the clocks were meticulously compared, the flying clocks were found to have measured slightly less time than the stationary ones by mere nanoseconds. The eastward travelling clocks lost time, while the westward travelling clocks gained time, all in precise accordance with Einstein's predictions. This wasn't time travel, but it was undeniable time dilation. The moving clocks experiencing a different inertial frame traverse time differently than the stationary ones. If you were to extrapolate this effect to its extreme, accelerating to near the speed of light, you could indeed travel thousands of years into Earth's future, while subjectively experiencing only a few years yourself. This is famously known as the twin paradox, though it's not a true paradox once relativity is properly understood. If one twin remains on Earth, while the other embarks on a relativistic journey to a distant star and back, the travelling twin will upon return have aged significantly less. They have in a very real sense travelled into the future by experiencing a compressed segment of time compared to their earthbound sibling. We observe this astonishing effect routinely in modern technology. The Global Positioning System, or GPS, relies absolutely on precise corrections for both special and general relativity. The satellites orbiting Earth at high speeds experience a slight slowing of their clocks due to special relativity. However, they are also further from Earth's gravitational field, which due to general relativity causes their clocks to run faster. The general relativistic effect dominates, resulting in the satellite clocks gaining approximately 38 microseconds per day compared to clocks on the ground. This might sound negligible, but light travels about 30 centimeters per nanosecond. Without these meticulous relativistic corrections, GPS navigation systems would accumulate errors of several kilometers per day, rendering them utterly useless. Every time you utilize GPS for navigation, you are in essence relying on our confirmed understanding of time dilation, on Einstein's profound insights into the nature of time. Particle accelerators provide even more dramatic, irrefutable confirmation. Muon's unstable subatomic particles generated when cosmic rays collide with Earth's upper atmosphere possess a fleeting half-life of roughly 2 microseconds. At the incredible speeds at which they are created, they should theoretically travel only about 600 meters before half of them decay. Yet we detect them abundantly at Earth's surface after they have traversed many kilometers. Why? Because from our reference frame, their internal clocks are running exquisitely slow. Time is dilated for them due to their extreme velocity. From their own perspective, if they possessed consciousness, the distance to Earth's surface would be contracted, allowing them to reach it within their brief lifetime. The same physics, just a different, equally valid perspective. We now routinely create muons in particle accelerators and observe them living far longer than their rest frame half-life dictates. The faster we accelerate them, the longer they persist from our macroscopic perspective. This is no longer a mere theory. It is a direct daily observation made in laboratories worldwide. Time genuinely, demonstrably depends on your motion and your position within a gravitational field. Now over the years, there have been numerous claims of individuals or organizations actively developing actual time travel technology. Most of these, it must be stated, are not credible. They invariably lack the fundamental theoretical foundation, the rigorous experimental evidence, or both. Yet there are serious physicists who have explored the practical aspects of time travel, even if the requisite technology remains far, far beyond our current grasp. Ronald Mallett, a professor at the University of Connecticut, has proposed an intriguing theoretical design using circulating laser beams to create a rotating cylinder of pure light that could, in principle, twist space-time sufficiently to generate closed time-like curves. The mathematics suggests it could work in principle, though the energy requirements would be truly astronomical, and significant questions remain about whether the effect would be robust enough to be practically useful. Mallett's motivation is deeply personal. His father died when he was young, and he has dedicated his career to finding a way to send a message back to his younger self, perhaps to warn his father to save him. It is a poignant reminder that beneath all the abstract physics there lie very human desires, sorrows, and aspirations. There has also been widespread speculation about whether highly advanced civilizations might have already conquered the problem of time travel. If temporal journeys are possible, and if civilizations can achieve a sufficiently advanced technological state, why do we not observe time travelers from the future walking among us? This is sometimes referred to as the temporal version of the Fermi paradox. Enrico Fermi famously asked, "Where is everybody?" referring to the apparent absence of extraterrestrial civilizations. We can with equal validity pose the same question about time travelers. Where are they? One potential answer is, of course, that time travel is simply impossible. That despite what general relativity seems to permit, there exists some deeper, currently unknown principle that fundamentally forbids it. Another answer suggests that time travelers do exist, but they meticulously conceal their presence to avoid any catastrophic disruption of history. This is the classic prime directive scenario from science fiction, and it's not entirely unreasonable. If you possess the power to travel through time, prudence would dictate extreme caution regarding any changes you might instigate. Or perhaps time travel is indeed possible, but only to points after the time machine itself is constructed. This is a common feature of many theoretical time travel proposals. If you create a wormhole time machine, you cannot by its very nature travel to a time before the machine was created. The wormhole only connects points in space-time after both of its mouths exist. Thus, we would not observe time travelers from our future because no one has yet built such a machine. They might arrive tomorrow or a century hence after we build one, but never before its creation. Stephen Hawking, with his characteristic wit, once hosted a party specifically for time travelers. He announced it after it happened, ensuring that only those capable of temporal displacement could have attended. No one showed up. He jokingly took this as empirical evidence that time travel isn't possible, but it is hardly conclusive. Perhaps no future time travelers were particularly interested in his party, or perhaps they did attend but remained perfectly hidden. Or maybe the conditions for time travel are so incredibly restrictive that casual social visits are simply impossible. Then there is the intriguing simulation hypothesis. The idea that our entire reality might be a sophisticated computer simulation created by an immensely advanced civilization. If our reality is merely a simulation, then time travel might become a simple matter of the simulators running the program backward or loading an earlier save state. From our perspective existing within the simulation, this would manifest as time travel, but from the outside it would be nothing more than elegant data manipulation. Nick Bostrom's simulation argument suggests that if civilizations can reach a stage where they can create detailed conscious simulations, and if they choose to do so, then the vast majority of conscious beings are likely residing within simulations rather than in the base reality. It's a strange and disorienting thought, but it connects to time travel in fascinating, almost inevitable ways. Let's delve a little deeper into retrocausality within quantum mechanics. Some interpretations of quantum mechanics, such as the transactional interpretation, developed by John Cramer, propose that quantum events involve waves travelling both forward and backward in time. When you perform a measurement on a quantum system, the act of measurement itself sends a wave backward in time, to the point where the system was initially prepared, and the intricate interaction of these forward and backward waves generates the outcome we ultimately observe. This sounds utterly bizarre, and it is, but it makes predictions identical to standard quantum mechanics, while potentially offering solutions to some of its conceptual problems. Experiments testing delayed choice quantum entanglement appear to show something akin to retrocausality at work. You make a choice about how to measure a photon after it has already passed through an apparatus, and yet the photon seems to have behaved as if it knew what choice you would make. This is not actual information travelling backward in time in a way that could be used to send messages to the past, but it profoundly suggests that the quantum world does not adhere to our conventional linear temporal ordering. Yakir Aharonov and his colleagues have developed a compelling framework called the two-state vector formalism, where a quantum system is described not by a single state, evolving forward from the past, but by both a state evolving forward from the past and a state evolving backward from the future. The present in this view is determined by this remarkable collaboration between forward and backward influences. It is a mathematically consistent way to conceptualize quantum mechanics, and it even makes some subtly different predictions from standard interpretations in certain exotic scenarios. A famous experiment, the quantum eraser, beautifully illustrates these mind-bending ideas. You set up a double-slit experiment with photons where interference patterns appear or disappear depending on which path information is available. But in the quantum eraser, you can erase or reveal this information after the photons have already passed through the slits, and even after they have been detected. When you meticulously analyze the correlated data afterward, it appears as if the photons knew what you would do in the future. They adjusted their past behaviour based on future actions. Again, this cannot be exploited to send classical information backward in time, but it fundamentally challenges our deepest intuitions about temporal sequence. These quantum experiments, while not yielding time machines, unveil a quantum realm where time is far stranger, far more fluid than in our macroscopic everyday experience. They hint that our deeply ingrained intuitions about cause-effect, past, present and future, might be mere emergent properties of large complex systems rather than fundamental immutable features of reality itself. And if that is indeed true, then perhaps in extreme conditions within the quantum gravity regime, or near the event horizons of black holes, or in the universe's incandescent infancy time, could behave in ways that utterly defy our current imagination. Let me briefly touch upon the psychological and philosophical implications of time travel, for they are as profound as the physics itself. If you could journey to your own past, would the you who arrived still be you? Personal identity is conventionally understood as a continuous thread, a seamless connection linking your past self, your present self, and your future self. But if that thread can loop back upon itself, if you could literally encounter your younger self, then the very concept of identity becomes incredibly complicated. Are you and your younger self the same person? You share a history, a memory up to a certain point, but then your experiences radically diverge. Philosophers have explored similar dilemmas like Derek Parfit's teletransportation paradox. If a machine scans your body atom by atom, destroys it, and then creates an exact replica on Mars complete with all your memories and personality, is that replica you? Most people's intuition wavers here. It feels like you in some sense, but is it the same you or merely a perfect copy? Time travel creates analogous, unsettling questions. If you meet a past version of yourself, that person will continue forward and eventually become the you that embarked on the journey. Yet in the moment of meeting, you are two distinct individuals with separate albeit intertwined experiences. Then there's the thorny question of moral responsibility. If you travel back and alter something, are you morally responsible for the ensuing consequences? In a many worlds interpretation, you are merely creating a new branching timeline where events unfold differently, and your original timeline remains unaltered. So you might not be harming your past, but you could be creating a new timeline filled with unforeseen suffering. Is that ethical? It presents a new variant of the classic trolley problem, the thought experiment in ethics about whether it's permissible to divert harm from many to a few. Some philosophers argue that the ability to travel through time would paradoxically rob life of its meaning. If mistakes can be instantly rectified, do our choices truly matter? But others counter that this assumes you would retain memory of the future when travelling to the past, which might not be the case, or that it assumes you can actually change things when perhaps you're always merely fulfilling what has already happened. The meaning of life in this view might be preserved even in a universe with time travel simply structured differently. Consider for a moment what it would feel like to experience a closed time-like curve to genuinely loop back and encounter yourself. The sensory experience would be profoundly disorienting in ways we can barely imagine. You would be occupying the same spatial coordinates as another version of yourself, breathing the same air, witnessing yourself from an external perspective. Which perspective would be real, both presumably? You would possess two simultaneous distinct experiences of the same moment, one as the older arriving temporal voyager, and one as the younger version being visited. And yet these experiences would eventually merge into a single memory, a single strand of consciousness that somehow integrates both viewpoints. Oliver Sacks, the renowned neurologist, wrote movingly about patients whose sense of time was severely disrupted by brain damage or disease. Some experienced moments as utterly disconnected, unable to form continuous memories. Others felt perpetually trapped in specific moments, reliving them repeatedly. These neurological conditions offer us a poignant glimpse into how utterly dependent our experience of time is on the proper intricate functioning of our brains. Time, as we subjectively feel it, is constructed by neural processes. It is an interpretation, a model our minds create from a continuous stream of sensory input and memory. This raises a fascinating, almost existential question. If time is partly a construct of consciousness, what happens to that construct under extreme relativistic conditions, astronauts orbiting Earth, experience minor, almost imperceptible amounts of time dilation, but they do not feel it. Their subjective experience of time remains entirely normal. But what if the dilation were extreme? What if you spent years traversing space at near light speed, experiencing only months subjectively? Would your consciousness adapt? Would you feel time passing differently, or would each fleeting moment still feel to your inner self like a normal moment? There is no way to know without actually experiencing it, and that remains for now far beyond our reach. The fastest humans have ever travelled is approximately 11 kilometers per second, achieved by the Apollo 10 crew. That is incredibly fast by terrestrial standards, but it is only about 0.0036% of the speed of light. The time dilation at such speeds is utterly negligible, immeasurable by human perception. To truly feel relativistic effects, you would need to achieve substantial fractions of light speed, 10%, 50%, and 90%. And we currently possess no propulsion systems remotely capable of achieving such velocities. Project Orion, conceived in the 1950s, was an audacious proposal to propel a spacecraft using controlled nuclear explosions. Small atomic bombs would detonate behind a massive pusher plate, and the ship would ride the resultant shockwaves. Design studies suggested it could reach a few percent of light speed, enough to make interstellar travel conceivable within human lifetimes. However, the project was ultimately abandoned, partly due to nuclear test ban treaties, and partly due to the sheer audacity and inherent danger of the concept. Yet the physics was sound. It could have been built. More recent theoretical proposals include antimatter rockets, where matter and antimatter annihilate to produce unimaginable amounts of energy, or Bussard ramjets, which would scoop up sparse hydrogen from the interstellar medium and use it as thermonuclear fuel. These remain purely theoretical, constrained by our inability to produce and store antimatter in useful quantities, and by the extreme engineering challenges of constructing a magnetic scoop large enough to gather sufficient fuel, but they are not fundamentally impossible. Given centuries of relentless technological development, such things might become feasible. And if they do, if humanity ever achieves near-light speed travel, then time travel into the future becomes a routine, almost mundane affair. Not science fiction, not wild speculation, but a matter of engineering. You would board a ship, accelerate to 99% of the speed of light, journey to a nearby star and back, and return to Earth decades or centuries later, having aged only a few years yourself. You would step off the ship into a future you could never truly return from, having left everyone you knew far behind in the past. This is the only form of time travel we are reasonably confident is possible, and it is in itself profoundly moving. It is a one-way journey forward, but it is real. The equations do not lie about this, and it means that in principle you could witness the far future of humanity, the evolution of our species, the ultimate fate of our home planet. You could observe how our civilization develops, whether we spread to the stars, whether we survive at all. You would be an ambassador from the past, carrying the ghosts and memories of a world that no longer exists except in the annals of history. Now, there's an interesting variant of this idea, sometimes called the cosmic clock. Different regions of the universe experience time at different rates, profoundly influenced by their motion and the local gravitational field. A civilization orbiting precariously close to a supermassive black hole, for instance, would experience time passing dramatically slower than a civilization residing far from any massive objects. This effect was vividly and remarkably accurately depicted in the film Interstellar, where a planet near a rapidly rotating supermassive black hole experienced such extreme time dilation that 1 hour on its surface equated to 7 years for distant observers. The science in that film was meticulously overseen by Kip Thorne, and indeed the time dilation near such a rapidly spinning black hole would be that extreme. This creates a compelling scenario where different parts of a galaxy could be fundamentally out of sync temporally. 1 million years might elapse in one region while only a few thousand pass in another. If civilizations exist in these diverse regions, they would inherently be travelling through time relative to each other, simply by existing within their home systems. One could even imagine a highly advanced galactic civilization deliberately utilising this principle, strategically parking ships in deep gravitational wells or accelerating them to relativistic speeds to effectively send colonists into the far future. It's a form of suspended animation, but achieved through the profound manipulation of physics rather than biology. When you arrived at your destination, the galaxy would have aged immeasurably more than you. New civilizations might have risen and fallen. Old ones might be distant legends. You would be a time traveller in all but name. Let us return to the ontological paradox, the information loop we briefly touched upon with the Shakespeare example, for its implications run far deeper. Imagine you receive the intricate blueprints for a time machine from your future self. You then meticulously construct the machine using those very blueprints, subsequently travel back in time and present the blueprints to your past self. The inescapable question remains, where precisely did the information contained within those blueprints originate? No one, it seems, invented it. It exists in a self-generating causal loop, utterly devoid of an apparent origin. This deeply violates our intuition so profoundly that many physicists adamantly believe it simply cannot happen, that nature must, by some as yet unknown principle, forbid such loops. Yet mathematically, such loops are perfectly permitted by general relativity. There is nothing in the equations that explicitly prevents information from existing without a clear origin. It is logically consistent, merely profoundly strange. And strangeness is not in the realm of fundamental physics synonymous with impossibility. Some researchers have speculated that quantum mechanics might offer a resolution. In quantum theory, information is inextricably linked to entropy and thermodynamics. The act of creating information invariably requires the dissipation of energy, a concomitant increase in entropy elsewhere in the universe. There exists a minimum energetic cost to computation and information processing inextricably tied to the second law of thermodynamics. This suggests that a self-generating information loop might be impossible, because it would violate thermodynamics demanding the existence of information without the entropic cost of its creation. But this remains speculative. We lack a complete unified theory of quantum gravity to provide a definitive answer. There's a beautiful, unsettling paradox in decision theory called Newcomb's problem that carries a similar temporal flavour. A superintelligent, omniscient predictor presents you with two boxes. One is transparent, clearly containing $1,000. The other is opaque and contains either $1 million or nothing. Crucially, the predictor has already made its decision on what to place in the opaque box based on its flawless prediction of your choice. If it predicted you would take only the opaque box, it placed $1 million inside. If it predicted you would take both boxes, it placed nothing in the opaque box. What do you do? This seems unrelated to time travel, yet it fundamentally is. The predictor's decision made in the past was directly contingent upon its knowledge of your future choice. There is a profound, albeit subtle, retrocausality implied. Your future decision, the act of choosing, appears to influence the past state of the boxes. Many find this paradox deeply troubling, and there is no universal consensus on the correct rational choice. It vividly illustrates our inherent discomfort with situations where future events exert influence over past conditions. Quantum mechanics and time travel might intersect in yet another fascinating way through the quantum Zeno effect. This is the astonishing observation that if you continuously measure a quantum system, you can effectively prevent it from evolving. The very act of measurement collapses the wave function, and if you measure frequently enough, the system becomes stuck in its initial state. It is named after Zeno of Elea, the ancient Greek philosopher, who proposed paradoxes about motion. Now, some physicists have speculated that if you attempted to create a closed time-like curve, quantum effects might subtly but powerfully prevent its formation through something akin to the quantum Zeno effect. The relentless build-up of vacuum fluctuations and quantum noise might become infinite at the precise point where the curve attempts to close effectively destroying the time machine before it can even function. Hawking's chronology protection conjecture in essence suggests something similar, that quantum effects conspire to prevent time travel even when classical general relativity seems to permit it. But we cannot know for sure because we lack the mathematical framework to calculate this reliably. String theory or loop quantum gravity might eventually provide the definitive answer, but for now it remains an open question. Nature might indeed protect chronology, or it might be far more permissive than we currently imagine, allowing for all manner of strange causal structures provided they satisfy some deep consistency condition we have yet to fully grasp. Let's pause to contemplate the energy requirements for these fantastical endeavours, for they are truly staggering. To create a traversable wormhole, even one barely large enough for a human, you would necessitate exotic matter with negative energy density. The Casimir effect, as I mentioned, produces minuscule amounts of negative energy, a mere whisper. To stabilise a wormhole of human scale, you would require enormous quantities of negative energy, potentially more than the total positive energy contained within an entire star. Some theoretical calculations suggest that the requirement could be reduced using specific geometries, perhaps creating a wormhole throat only a few meters across, but utilising quantum effects to ensure safe passage. Yet even these optimised designs demand energy manipulations far, far beyond our current technological prowess. We are speaking of engineering space-time itself bending and twisting the very fabric of reality. It is a godlike power that may forever remain beyond our reach, unless of course nature itself provides cosmic shortcuts. If wormholes exist naturally, perhaps as primordial remnants from the incandescent chaos of the Big Bang, we might one day find one rather than having to build one. Primordial wormholes, if they exist, would likely be extraordinarily small and fleeting in most models, but perhaps some could have been stabilised by unique conditions in the early universe, conditions we do not yet fully understand. Finding one would be akin to discovering a pre-existing door to elsewhere, and elsewhere simply waiting for us to cross its threshold. The search for such exotic phenomena is an active part of modern astrophysics. Gravitational wave observatories like LIGO and Virgo are already detecting ripples in space-time from colliding black holes and neutron stars. Future observatories with enhanced sensitivity might be capable of detecting the subtle signatures of wormholes or other unusual space-time structures should they exist. The data might be hiding in plain sight, waiting for us to develop the conceptual lenses to recognize it. There's an aspect of time we haven't fully explored yet, its intimate relationship with consciousness and memory. Our subjective experience of time is inextricably bound to how we remember the past and anticipate the future. The past exists for us as memory, a narrative woven from fragments of what was. The future exists as imagination, a canvas of possibilities. The present moment, this instantaneous now, we believe ourselves to be experiencing is in fact an intricate construct, meticulously assembled by our brains from sensory data that arrives at slightly different times. Vision, for instance, takes longer to process than touch. Our brains seamlessly synchronize these disparate inputs to create the illusion of a unified, continuous present moment. Studies of perception indicate that what we subjectively experience as now actually encompasses a temporal window of about 3 seconds. Our brains integrate information over this brief window to create the cohesive sensation of the present. This is precisely why music resonates with us, why we can perceive rhythm and melody. Individual notes separated by more than about 3 seconds tend to feel disconnected, but within that window they flow together, creating a pattern. Subjective time at the level of consciousness possesses a granularity, a texture that is determined by the speed and complexity of our neural processing. What then would happen to this subjective constructed time if you journeyed through a wormhole or orbited precariously close to a black hole's event horizon? Would your conscious experience of the present moment stretch or compress? Would you feel time passing differently, or would everything appear normal to you while the external universe aged rapidly? These are not merely philosophical conundrums. If we ever realize time machines or achieve extreme time dilation, humans will inevitably experience these conditions, and we will need to profoundly understand their impact on human consciousness. There are hints from experiments with altered states of consciousness. Individuals who have ingested certain psychedelics frequently report that time seems to stretch or compress, that hours can feel like minutes or minutes like hours. Neuroscientists studying these experiences have observed profound changes in brain connectivity and processing that might explain these temporal distortions. The brain's internal clock, the intricate mechanism that judges duration, can be accelerated or decelerated by altering neural activity. This suggests that subjective time is plastic, profoundly malleable, dependent on the brain's state, rather than some absolute external flow. If this is true, then perhaps the experience of time travel would be less jarring than we imagine. Your brain might adapt, adjusting its temporal processing to maintain a semblance of normalcy, even under extreme conditions. Or perhaps it wouldn't. Perhaps you would experience profound dissociation, a terrifying temporal disorientation. We cannot know until someone tries, and that remains a distant prospect if it ever happens at all. Let me return to the arrow of time in cosmology, for it connects to some of the deepest, most foundational questions about why the universe is precisely the way it is. The early universe, in the fleeting moments after the Big Bang, existed in an extraordinarily low entropy state. Everything was unimaginably hot, dense, and remarkably uniform, a nearly perfect plasma of fundamental particles and radiation. As the universe expanded and gradually cooled, this initial pristine uniformity began to break down. Matter clumped together to form stars and galaxies, and entropy inevitably increased. This process, this relentless movement from low entropy to high entropy, generates the arrow of time we so profoundly experience. But why was the initial entropy so extraordinarily low? This remains one of the greatest unsolved problems in all of cosmology. A truly random configuration of the universe would by definition represent maximum entropy, a cold, diffuse soup of particles with no structure, no stars, no galaxies, nothing interesting happening whatsoever. The fact that our universe began in such a remarkably special low entropy state seems to demand a profound explanation. Some physicists, like Roger Penrose, have proposed that there might be a fundamental law or principle that constrains these initial conditions, something that requires the universe to begin in a low entropy state. Others suggest that we are simply viewing the problem incorrectly, that our universe might be just one small region within a vast infinite multiverse where different regions possess different initial conditions. We simply happen to reside in a region with low initial entropy, because those are the only regions where complex structures like stars, planets, and crucially life can form. It is a selection effect, an anthropic argument. We observe a low entropy beginning because we could not possibly exist to observe anything else. If the multiverse picture is indeed correct, there might exist regions where time literally runs backward, where entropy decreases instead of increases. To hypothetical inhabitants of such regions, if conscious observers could even exist under such conditions, time would flow in the opposite direction. Their past would be what we call the future, and their future what we call the past. And if by some impossible means you could travel between these regions, what would that experience truly be like? Would you feel yourself unliving, unthinking, memories forming in reverse? Probably not, because consciousness, as we understand it, appears to intrinsically require an increase in entropy. The continuous formation of new memories, new information states within the brain. A mind running backward in time would likely not be conscious in any recognizable sense. It would be akin to watching a film in reverse. The physical process might occur, but the meaning, the narrative, would be utterly inverted. So even if backward time regions exist within the multiverse, they would likely be devoid of conscious observers, at least as we comprehend consciousness. The heat death of the universe, that distant chilling future when entropy finally reaches its maximum, and nothing interesting can ever happen again, represents a kind of end to time in any meaningful sense. Time might technically continue as a coordinate, as a dimension one could theoretically traverse. but there would be no events to mark its passage, no change, no structure. It would be a timeless stasis, not because time doesn't exist, but because nothing happens. Is that fundamentally different from time not existing at all, philosophically? Perhaps not. Some profound cosmological models, like the conformal cyclic cosmology, proposed by Roger Penrose, suggest that the heat death might not be the ultimate end. Instead, the universe might pass through this maximum entropy state into a new phase that is mathematically equivalent to another Big Bang. Time in this audacious vision doesn't end. It recycles eternally. The eons after heat death become indistinguishable from the moments after a new beginning, because there is no structure, no scale, nothing to differentiate between the unimaginably large and the infinitesimally small. In this cyclical picture, the universe undergoes infinite cycles, each one lasting trillions upon trillions of years, with the far future of one cycle seamlessly becoming the Big Bang of the next. It is a beautiful, almost spiritual idea, and it even makes some observational predictions related to subtle patterns in the cosmic microwave background radiation. The data so far is ambiguous, open to interpretation, but it is being rigorously studied. If Penrose's vision is correct, then time is eternal in a cyclical sense, and perhaps faint echoes of previous cycles could be detected if we only knew how to listen. Now, time travel in fiction often conjures images of gleaming machines replete with flashing lights and spinning components, a testament to intricate engineering. But the deeper physics suggests that if time travel is possible at all, it is far more about geometry than machinery. You would not simply build a device that moves through time, you would astonishingly engineer space-time itself into a specific configuration that permits temporal loops. This is profoundly different from how we typically conceive of technology. Most of our innovations operate by manipulating matter and energy by cleverly arranging atoms. But manipulating space-time demands working with gravity, with the very curvature of reality itself. It is an entirely different order of capability. You would require control over colossal amounts of energy, directed with unimaginable precision. You would need to understand quantum gravity intimately enough to avert catastrophic consequences, such as inadvertently creating a runaway black hole, or tearing an uncontrollable hole in space-time. The Alcubierre drive, which I mentioned earlier, vividly illustrates this. You're not propelling a ship through space with rockets. You're instead contracting the space in front of it and expanding the space behind it, creating a bubble that surfs on a wave of space-time distortion. The ship, nestled comfortably inside this bubble, experiences no local acceleration. Space itself moves around it. This is such a fundamentally different approach to travel that it demands a complete re-evaluation of what we mean by movement and distance. And if you could achieve such precise manipulation of space-time, then you would be approaching truly godlike capabilities. You could create regions where time flows at dramatically different rates, sculpt pocket universes with their own bespoke physical laws, or forge bridges between distant parts of the cosmos. You would quite literally be sculpting reality itself. This profound capability is sometimes termed metric engineering, and it is the subject of serious, albeit highly theoretical papers in physics, despite the immense practical challenges. Some scientists speculate that truly advanced civilizations might engage in this routinely. Rather than constructing physical structures from matter, they might build structures from space-time itself. Imagine a Dyson sphere not of metal, but of exquisitely curved space-time collecting energy by tapping into vacuum fluctuations or zero-point energy. Or a habitat where time flows slower within granting its inhabitants vastly more subjective time per unit of external time. These are ideas that emerge from taking general relativity seriously and asking what becomes possible if one possesses sufficient energy and control over the fundamental fabric of existence. Frank Tipler, in his work on the Omega Point, proposed a cosmological model where a sufficiently advanced civilization could engineer the far future of a collapsing universe to achieve infinite computational capacity. In this model, As the universe contracts, it does so unevenly, generating chaotic dynamics that could be harnessed for computation. The oscillations between different regions would become exponentially faster, allowing an infinite number of computational steps in a finite subjective time before the final singularity. In such a scenario, consciousness could continue forever in subjective time, even as external time approached an absolute end. It is a highly speculative idea, heavily reliant on specific cosmological assumptions that current observations which favour a perpetually expanding universe may not support. Yet Tipler's work beautifully illustrates how time consciousness computation and cosmology can interweave in profoundly unexpected ways. What time truly means depends fundamentally on what kind of universe we inhabit, and what level of mastery over physical law is ultimately achievable. I find myself continually returning to this pivotal question: is time fundamental or is it emergent? In the realm of everyday physics, we treat time as a given and absolute background against which events unfold. But in quantum gravity, time might emerge from something far more basic. Carlo Rovelli, whom I mentioned earlier, speaks of thermal time, the radical idea that time arises from thermodynamics, from the coarse graining of quantum states. What we perceive as time in this view is intrinsically linked to our ignorance to the fact that we do not track every single quantum degree of freedom within a system. If this is correct, then at the most fundamental level there is no inherent time, only intricate quantum correlations between states. Time appears only when we zoom out, when we consider macroscopic averages rather than microscopic details. It is analogous to how temperature emerges from molecular motion. Individual molecules do not possess temperature. They possess velocity and kinetic energy. Temperature is a statistical property, an emergent phenomenon of large collections of molecules. Similarly, time might be a statistical property that emerges when large collections of quantum states interact. What fascinates me about this emergent view of time is its potential to resolve some of the deep-seated tensions between quantum mechanics and general relativity. In quantum mechanics, as I've noted, time is treated as an absolute unyielding background parameter. It ticks away uniformly, measuring the evolution of quantum states. But in general, relativity time is profoundly dynamical. It curves, warps, and twists an integral part of the geometry of space-time. These two pictures do not naturally fit together. One asserts time is absolute, the other that it is relative. And yet we know both theories are extraordinarily successful within their respective domains. So they must, at some deeper level, both be approximations to a more fundamental truth. Julian Barber's timeless physics pushes this even further. He proposes that the universe is in essence a vast space of all possible configurations, what he calls Platonia. Each point in Platonia represents a complete configuration of everything in the universe at what we would conventionally call an instant. But in Barber's radical view, all these configurations exist timelessly. They do not flow from one to another, they simply are. What we perceive as time is the profound fact that these configurations possess structure. They form sequences that our minds interpret as temporal flow. Think of it like frames in a film. Each frame exists independently, static, timeless. But when projected in sequence, the illusion of motion and change miraculously appears. Similarly, the configurations in Platonia might form intricate paths, and conscious beings embedded within those configurations would perceive themselves as moving along such a path, experiencing time. But from an external vantage point, from the perspective of Platonia as a whole, there is no true motion, no flow, only structure. This is profoundly counterintuitive, I know. It feels intrinsically wrong, because time seems so undeniably real, so immediate to our experience. But many things that feel real are in fact constructs. Colour, for instance. There is no such thing as red or blue in the fundamental physics of light. There are merely electromagnetic waves of different wavelengths. Our brains interpret certain wavelengths as red, others as blue. The colour resides in our perception, not in the light itself, Barber suggests that time is analogous, a perceptual construct that arises from the underlying structure of physical reality, rather than being fundamental to it. If he is correct, then time travel paradoxes simply dissolve, because there is no linear flow of time to disrupt. You cannot change the past because past and future are simply different, equally real regions of Platonia. You could potentially access different regions, experience them in unusual orders, but you could no more alter them than you could alter the number 5 by merely thinking about it. The structure is what it is timelessly, yet this creates its own profound puzzles. If everything exists timelessly, what determines which configurations are connected into the specific path we perceive as our universe's history? Why this sequence rather than some other Barber offers answers involving quantum mechanics and probabilities, but they are complex and not universally accepted. It is a framework that confronts the problem of time head-on and offers radical solutions, but whether those solutions are correct remains an open, vigorous debate. Let's momentarily shift our focus to something more concrete: the intimate relationship between information and time. Information theory, pioneered by Claude Shannon in the 1940s, provides us with powerful mathematical tools for quantifying information, and there exists a profound connection between information and entropy, discovered by Shannon and later meticulously developed by physicists like Rolf Landauer and Charles Bennett. Erasing information, it turns out, inherently requires dissipating energy, thereby increasing entropy. There is a minimum energetic cost to any form of computation and information processing intrinsically tied to the second law of thermodynamics. This means that time's arrow, the relentless increase of entropy, is deeply connected to the very act of information processing, to memory and to computation itself. Every time you form a memory, you're in a very subtle but real sense increasing the entropy of the universe. The neural changes that encode that memory are irreversible processes that dissipate heat. Consciousness, which involves ceaseless information processing, is by its very nature an entropy-generating process. We are in a very real sense beings made of increasing entropy, perpetually surfing the wave of the second law. If you were to travel backward in time, what would happen to your memories? Would they persist, implying that you would accumulate information as you move toward the past, seemingly violating thermodynamics? Or would your memories progressively erase themselves as you journeyed backward so that you would arrive in the past with no knowledge whatsoever of the future? The latter seems more consistent with the known laws of physics, but it would render the act of time travel rather pointless. You wouldn't even know you had travelled. You would simply find yourself in what appears to be the past with no explanation for your inexplicable presence. Unless, of course, information can somehow be preserved in a way that doesn't violate thermodynamics. Perhaps memories could be encoded in quantum states that do not contribute to entropy in the usual way. Or in a many-world scenario, the information might travel with you to a new branching timeline, where thermodynamics begins afresh. These are deep speculations, but they vividly illustrate how even contemplating time travel seriously forces us to confront fundamental questions about information entropy and the very structure of physical law. The holographic principle, which I touched upon earlier, suggests that all the information within a volume of space is astonishingly encoded on its boundary. This profound insight emerged from the study of black holes, where Jacob Bekenstein demonstrated that the entropy of a black hole is proportional not to its volume but to the area of its event horizon. This was initially deeply surprising. One would intuitively expect entropy to scale with volume, as it should count the number of possible states of everything inside, but for black holes it scales with surface area. Leonard Susskind and Gerard 't Hooft later generalized this, proposing that this principle holds true more broadly, that the universe itself might be holographic in some profound sense. All the information about what transpires within a region of space might be entirely encoded on the boundary of that region. If this is correct, then the three-dimensional space we perceive might be a kind of projection from a two-dimensional information structure. We would in essence be living in a hologram. What might this mean for time travel? Well, if information about all events is intricately encoded on these boundaries, then perhaps the entire history of a region is in some sense accessible from that boundary. You wouldn't need to physically travel through time, you would merely need to decode the holographic information corresponding to different moments. This is highly speculative, but it suggests that the past might not be truly gone, but rather subtly encoded within the fundamental structure of space-time in ways we could potentially access with sufficient understanding and technology. Quantum entanglement also offers intriguing, almost mystical possibilities. When particles become entangled, they share a unified quantum state instantaneously, across any distance, defying classical notions of locality. Einstein, as we've noted, was deeply troubled by this, believing it violated the principle that distant events should not influence each other faster than light. Yet rigorous experiments have repeatedly confirmed that entanglement is demonstrably real. You can measure an entangled particle here and instantaneously gain certain knowledge about its partner, even if it is light years away. Some physicists have even proposed a radical connection between entanglement and space-time geometry itself. The ER-EPR conjecture, named after Einstein-Rosen-Bridges wormholes, and Einstein-Podolsky-Rosen-EPR entanglement, suggests that entangled particles might at a deep level be connected by tiny ephemeral wormholes. If that audacious conjecture is true, then space-time might be stitched together by a vast, intricate network of quantum connections, and these connections might provide pathways that bypass normal space-time separation. Could you utilize entanglement to travel through time? Probably not directly, because you cannot transmit classical information faster than light using entanglement alone. Measuring one particle does not allow you to control the state of its partner. But perhaps in combination with other exotic effects with profoundly curved space-time or the presence of exotic matter entanglement, could play an unforeseen role in time travel mechanisms we have yet to even imagine. There is also the profound question of whether the fundamental constants of nature might vary over time: the speed of light, the strength of gravity, the masses of fundamental particles. We typically assume these are truly constant, immutable, identical everywhere and at all times. Yet some subtle cosmological observations have hinted that certain constants might have been slightly different in the early universe. The fine structure constant which governs electromagnetic interactions might have varied by minute amounts over billions of years. If these fundamental constants can indeed change, then the very nature of time itself might have been different in different cosmic eras. The early universe, governed by potentially different physical laws, might have permitted phenomena that are utterly impossible now. Perhaps time travel was intrinsically easier then, when space-time was more malleable, more energetic, or perhaps it will become easier in the far future under conditions we cannot yet predict. The laws of physics as we currently know them might be local in time as well as space, valid for our specific epoch, but subtly different elsewhere in the universe's grand history. I find myself thinking about the intrepid explorers of previous centuries who set sail for distant unknown lands, encountering environments and conditions utterly unlike anything they had ever known. The crushing pressures of the deep ocean, the frozen desolation of the polar regions, the thin, unforgiving air of the high atmosphere. Each new frontier demanded new understanding, new adaptations, new ways of perceiving reality. Time travel, if it is ever truly possible, might be like that. Not merely a journey to a different when, but a journey to a fundamental regime where the rules are subtly or even dramatically different, where our present intuitions utterly fail, where we require entirely new conceptual frameworks to make sense of what we are experiencing. And perhaps that deeper understanding is the real frontier, not merely space but time itself. We have dispatched probes to every planet in our solar system, landed on distant asteroids, and gazed back to nearly the very beginning of the universe with our telescopes. But we have barely scratched the surface of time, experiencing it only in its forward linear flow at our normal accustomed rate. What wonders, what profound insights might await us in the other directions? The backward paths, the sideways branches, the bewildering loops and tangles that mathematics so tantalizingly suggest could exist. Or perhaps time travel remains forever impossible, a tantalizing mathematical possibility that nature ultimately vetoes through some deep, overarching principle we do not yet comprehend. Perhaps we are intrinsically meant to be temporal beings, irrevocably locked into experiencing moments in an unyielding sequence one after another, forever unable to revisit or preview. There might be a profound wisdom in that limitation, a fundamental reason woven into the very fabric of reality itself. Still, the act of questioning matters, the relentless attempt to understand matters. Every time we probe the elusive nature of time, we learn something profound about existence itself, about causality, consciousness, and the ultimate structure of the universe. Whether or not we ever construct a functional time machine, the arduous journey of trying to understand whether it's possible takes us to the deepest truths physics has to offer. The question of free will becomes particularly acute and painful when we consider the implications of time travel. In a normal linear timeline, one flowing perpetually forward, without loops or branching paths, we can at least maintain the comforting illusion that our choices possess genuine agency, that we're truly deciding between multiple possible futures. But introduce time travel, and this illusion becomes far more difficult to sustain. If future events can in some profound way influence past decisions, if closed time-like curves imply that what will happen has in some deeper sense already happened, then where does genuine choice fit into this preordained tapestry? There was a physicist named John Wheeler, the same visionary who proposed delayed choice experiments, who coined the term black hole, and mentored countless influential physicists who held a deeply participatory view of the universe. He suggested that observers do not merely witness reality, they actively help bring it into being through their observations and choices. In quantum mechanics, before you measure a particle, it exists in a superposition of states. The act of measurement collapses this superposition into a definite outcome. You, the observer, actively participate in creating the specific reality you observe. Applied to cosmology, Wheeler proposed what he called the participatory anthropic principle. This radical idea suggests that observers in the present might be fundamentally necessary to give meaning to the past, to retroactively collapse the quantum wave function of the early universe through our very observations. It is a profound concept suggesting that consciousness and choice are not merely passive phenomena emerging from physics, but active, indispensable ingredients in shaping reality itself. And if that is true, then perhaps free will survives even in a universe replete with time travel, because choices genuinely create outcomes rather than simply revealing predetermined results. But not everyone agrees with Wheeler's interpretation. Many physicists prefer interpretations of quantum mechanics that do not grant observers a special status, where the wave function never truly collapses, or where collapse is merely an artifact of decoherence, the continuous interaction with the environment. In these views, reality is objective and deterministic at some fundamental level, and our subjective sense of making choices is an evolved perception, rather than a fundamental feature of the universe. Compatibilism, a school of thought in philosophy, attempts to reconcile free will with determinism by redefining what free will truly means. In this view, you possess free will not in the sense that your actions are uncaused, but in the sense that they arise from your own desires, beliefs, and reasoning processes rather than from external compulsion. Even in a deterministic universe, or one containing closed time-like curves, you would still possess free will, in this compatibilist sense, because your choices would still be yours, still flowing organically from who and what you are. I find there is something satisfying about this view, though I am not certain it fully captures what we intuitively mean by free will in our everyday experience. When you genuinely deliberate about a decision, it truly feels as though the future is open, as though multiple possibilities exist and you are actively selecting among them. Compatibilism asserts that this feeling is real enough. It does not matter whether the selection was ultimately determined by prior causes, as long as those causes include your own unique mental processes. Perhaps that is sufficient. Perhaps we do not require metaphysical freedom, only psychological freedom. Time travel forces these intricate philosophical issues into sharp relief because it makes the determinism explicit. If you meet your future self, then clearly your future is at least in its broad strokes fixed. You will become that person. You will perform the actions they remember doing. Yet moment to moment you still possess the profound experience of choosing, of deliberating. So which is real, the fixedness or the freedom? Perhaps both in different complementary senses. Perhaps the timeline is fixed when viewed from outside time from the perspective of Platonia or the block universe, but experienced as open and malleable when lived from within. This is sometimes called the tenseless view of time versus the tensed view. The tenseless view declares that all moments are equally real, past, present, and future. The tensed view insists that only the present is truly real, that the past no longer exists, and the future has not yet materialized. We profoundly experience time in the tensed way, but physics increasingly suggests the tenseless view is correct. Let me briefly speak about causal loops in nature instances where we observe something akin to circular causation, even without invoking explicit time travel. In quantum mechanics, you can encounter situations where event A influences event B, and event B simultaneously influences event A through entanglement. The causal structure becomes cyclic or even circular when viewed from certain perspectives. These are not exact time travel loops, but they demonstrate that nature already possesses resources for nonlinear causation that we are only just beginning to comprehend. There are also intricate feedback loops in complex systems, ecosystems, economies, or neural networks where effects circle back to influence their own causes. A forest fire creates conditions that make future fires more likely. Economic inflation triggers wage demands that in turn cause further inflation. Neural activity creates patterns that reinforce themselves. These are not violations of causality, but they vividly illustrate how causes and effects can interweave in complex ways that defy simple linear chains. When we contemplate time travel, we might be too narrowly focused on the simplistic cases like the grandfather paradox. Real causation in complex systems is inherently messy, replete with feedback and circular influences. Perhaps time travel, if it exists, would create causal structures that appear similarly messy, challenging to analyze but not actually paradoxical. Perhaps the universe is robust enough to gracefully handle these complications, absorbing them into its overall consistency without fundamentally breaking. There's a fascinating concept in mathematics called fixed point theorems. These are theorems that state that under certain conditions a function must possess a point where it maps to itself, where f(x) equals x. The Novikov self-consistency principle is in essence a fixed point requirement for time travel. The timeline must be consistent with itself. It must be its own fixed point in configuration space. Mathematical fixed point theorems guarantee that such solutions exist under broad conditions, which suggests that consistent time travel timelines are indeed mathematically possible, even if physically realizing them is impossibly difficult. David Deutsch, whom I referenced earlier, has applied quantum computation theory to the challenges of time travel. He has demonstrated that quantum computers, when operating in the presence of closed time-like curves, would possess extraordinary computational power, capable of solving problems that are utterly intractable for normal quantum computers. Essentially, you could send information back in time to assist in solving a problem using the answer from the future to generate the answer in a self-consistent loop. It is akin to looking up the answer in the back of a book, except you are the one who wrote the book utilizing knowledge gained from the future. This, strangely enough, does not violate physics. The computation naturally finds a fixed point where the information loop is self-consistent. There is a unique solution that makes the loop work, and the quantum computer intrinsically evolves toward that solution. Deutsch has even proposed experiments to test this principle using simulated closed time-like curves in quantum systems. Some initial experiments have been performed, and they confirm the basic predictions, though of course these are not actual time travel, but rather quantum systems meticulously engineered to behave mathematically as if they were. The implications are truly stunning. If this technology could be scaled up a civilization with access to closed time-like curves could solve problems instantly that would otherwise require longer than the age of the universe. They could factor enormous numbers, break any encryption, simulate incredibly complex systems perfectly. They would possess a form of computational omniscience within the strict bounds of physical law. Of course, they would still be constrained by consistency requirements. They could not solve logically impossible problems or create true paradoxes. But within those fundamental constraints, their power would be nothing short of godlike. I sometimes wonder whether the universe itself might be engaged in something akin to this. Quantum mechanics at its heart involves summing over all possible paths a particle could take all possible histories. What if the universe is in some profound way computing its own evolution by exploring all possibilities and converging upon the consistent solution? Time in such a scenario would not flow in a simple linear way, but would emerge from a timeless computation that identifies the self-consistent structure. This is vague, I know, more poetry than physics, but it gestures toward possibilities for which we might not yet possess the appropriate language. The Wheeler-DeWitt equation in quantum cosmology, an audacious attempt to describe the wave function of the entire universe, is remarkably devoid of time. It is a timeless equation describing a timeless state. Time in this context emerges somehow from the quantum correlations within this state, from the way different parts of the universal wave function relate to each other. Fully solving the Wheeler-DeWitt equation remains far beyond our current mathematical abilities, but its very existence suggests that time might not be fundamental even in quantum mechanics when applied to the universe as a whole. If time emerges, then perhaps it emerges differently in different contexts or regimes. Perhaps within black hole interiors or at the Big Bang singularity, time does not emerge in the usual way, and we consequently encounter structures that appear paradoxical from our perspective, but are entirely natural within those specific regimes. Perhaps time travel isn't truly travel at all, but rather access to regions where time possesses a different structure, where our usual rules simply don't apply because they were always approximations valid only under particular circumstances. This leads me to a subtle but crucial point about language and concepts. We are deeply accustomed to using words like travel, past and future, and these words carry inherent implicit assumptions about how time fundamentally works. When we attempt to describe scenarios where time operates in a radically different manner, we are inherently handicapped by a language specifically designed for normal, linear temporal experience. It is akin to trying to describe the vibrant nuances of colour to someone who has been blind from birth, or the soaring complexities of music to someone who has never heard a sound. The concepts simply do not fit neatly. Physics frequently encounters this profound problem. Quantum superposition entanglement, curved space-time extra dimensions. These are all phenomena that lack good intuitive analogies in our everyday experience. We resort to metaphors and the rigorous precision of mathematics, but the metaphors are always slightly insufficient, always slightly wrong, and the mathematics, while precise, does not always convey intuitive understanding. Time travel, if it exists, might be similar, something that can be precisely described mathematically, but never quite captured in words or mental images that feel entirely right or intuitive. Perhaps future humans or highly advanced artificial intelligences or whatever comes after us will think about time in ways we cannot currently imagine. They might possess cognitive structures or computational frameworks that render time travel seemingly natural, even obvious. They might look back at our present confusion with the same perspective we adopt when looking back at ancient peoples, grappling with basic mechanics or chemistry, not because they were unintelligent, but because they lacked the necessary conceptual tools to think clearly about phenomena utterly outside their direct experience. Or perhaps time travel will remain forever confusing a phenomenon that can never be fully domesticated into human intuition, no matter how much we study it. Some things in physics are like that. Quantum mechanics has existed for over a century, and physicists still passionately debate its meaning, how to interpret its elegant mathematics. The formalism works perfectly. Its predictions match experiments with extraordinary precision, but but the underlying reality it describes remains profoundly obscure. Time travel might exist in a similar liminal space technically possible perhaps, but never truly understood. There is a curious asymmetry in how we conceptualize space versus time. We readily accept that we can move freely through space forward and backward, left and right, up and down. No one finds this paradoxical or mysterious, but time we can only move through in one inexorable direction at one unyielding rate. We are trapped in its flow, swept along from past to future at precisely 1 second per second. Why should time be so fundamentally different from space? After all, relativity explicitly tells us they are unified into space-time, that they are inseparable aspects of the same underlying structure. The answer, as I've mentioned, seems to lie in thermodynamics in entropy and the overarching arrow of time. Space does not possess an arrow. There is no thermodynamic principle that favours north over south or up over down. But time does possess an arrow globally, at least, because the universe began in an exceptionally low entropy state and is inexorably evolving toward higher entropy. This asymmetry, this inherent directionality in time, renders it fundamentally different from space in terms of our experience and our physics. But locally in small regions and over short timescales, the arrow of time can become ambiguous, almost imperceptible. If you filmed molecules in a gas for a microsecond, you would be unable to tell if the film was running forward or backward. The molecular dynamics are inherently time-symmetric. It is only over longer periods, as entropy statistically increases, that the direction becomes clear. So there might exist regimes, extreme conditions, where the arrow of time is weak or even absent, where time might become more space-like. And perhaps in those regimes, movement through time could be less constrained. Inside black holes, for instance, the roles of time and space profoundly swap in a conceptual sense. Outside a black hole, you can maintain the same spatial location by applying thrust by actively fighting gravity, but you cannot help but move forward in time. Inside the event horizon, according to the austere mathematics, you cannot maintain the same radial position no matter how much thrust you apply. You inevitably move inward toward the singularity, but the time coordinate itself becomes space-like. Does this imply that you could effectively move backward in time inside a black hole? The mathematics remains ambiguous, and we cannot observe it directly, so we simply do not know. Kip Thorne and other brilliant minds have explored these internal geometries extensively. The rotating Kerr black hole in particular possesses an even more complex interior structure, with rings, singularities and regions where closed time-like curves might theoretically exist. However, the tidal forces within such a region would be undeniably lethal, and the geometry itself might be inherently unstable, collapsing before any hypothetical voyager could exploit it. Yet the mathematics permits these structures, which means nature, at least in its abstract potential, contemplates the possibility of such exotic space-time geometries. I often think about the sheer courage it would demand to test time travel if we ever developed the requisite technology. You would be volunteering to be the first human being to potentially violate causality as we understand it, to create or encounter a paradox. Even if the theory proclaimed it was safe-asserted that consistency would be miraculously maintained, would you truly trust that? Would you step into a wormhole or a closed time-like curve, not knowing for certain what would emerge on the other side or whether you would emerge at all? The early astronauts, of course, possessed a similar brand of courage. They climbed into rockets built, as the saying goes, by the lowest bidder, keenly aware that many test flights had exploded, knowing the profound risks. But time travel would be different. It would not merely be your life at stake, but potentially causality itself, the very logical structure of reality. A malfunction would not just kill you, it might create a paradox that, well, we simply do not know what would happen. Would the universe subtly prevent it? Would you spawn an entirely new timeline? Would reality itself somehow glitch or shatter? The consequences of failure are quite literally impossible to predict. Perhaps that is precisely why, if time travel is possible, we have not observed travellers from the future. Perhaps every civilization that develops the technology is simply too cautious to deploy it. Or perhaps they attempt it once something goes catastrophically wrong, and in that specific timeline they cease to exist or lose the capability to try again. We might simply be existing in a timeline where time travel is never successfully deployed, even though it remains theoretically possible. The successful deployments in this view occur in other branches of the multiverse that we cannot access or observe. There is also the possibility that time travelers are in fact here among us, but perfectly undetected. If you journey to the past, you would exercise extreme subtlety, observing without interfering. You would adopt period clothing, assimilate period mannerisms, and blend seamlessly into the historical tapestry. Perhaps people we now regard as eccentric geniuses or uncanny predictors were in reality time travelers equipped with knowledge of the future. Leonardo da Vinci sketching helicopters and submarines centuries before their invention. Nostradamus making predictions that appear remarkably accurate in retrospect. Perhaps just perhaps. But these are delightful speculations, utterly devoid of empirical evidence, and they require a conspiracy level of thinking to sustain. The simpler explanation is that genius exists that individuals can be profoundly ahead of their time through sheer intelligence and imagination alone, without needing literal temporal displacement. We should always remain skeptical of extraordinary claims absent extraordinary evidence. Yet the idea captures something profoundly important about how we think about time and knowledge. We yearn to see the future, to possess the power to alter the past. It is a deep, primal human desire reflected in countless myths and stories. The oracle at Delphi foreseeing the future, Orpheus descending into the underworld to retrieve Eurydice from the past. The ability to transcend temporal limitations is consistently portrayed as divine, as beyond human capability. And perhaps it is. Perhaps time travel truly belongs in the realm of gods and myths forever beyond the reach of physical law. But I am not yet ready to accept that conclusion. Physics has surprised us too many times, unveiled possibilities we never imagined. A mere century and a half ago, physicists confidently believed they had unravelled nearly everything, that only minor details remained to be ironed out. Then came relativity and quantum mechanics, and the universe revealed itself to be far stranger, far more wondrous than anyone had ever dared to dream. We are likely still in a similar position today. We possess some knowledge, but vast territories of ignorance remain, particularly concerning quantum gravity and the deepest, most fundamental nature of space-time. When we finally possess a complete theory of everything, or at least a theory of quantum gravity that seamlessly unifies general relativity and quantum mechanics, it might definitively inform us about time travel. It might declare, yes, here is precisely how it works, here are the specific rules. Or it might pronounce, no, here is precisely why it is impossible. Here is the fundamental principle that forbids it. Either answer would be profoundly significant. Either answer would teach us something absolutely fundamental about the universe. Until then, we reside in this strange liminal space where time travel is mathematically possible, yet practically implausible, permitted by the equations, yet perhaps forbidden by some deeper, as yet undiscovered principle. It is a space of uncertainty, of boundless wonder, of exhilarating possibility. And in many ways, that open-endedness is far more exciting than knowing for sure. The question remains open, and open questions are the very engine that drives science forward. Let me share one more elegant theoretical proposal, a particularly refined one, the Roman ring conceptualized by Thomas Roman. Imagine an ordinary cosmic string which I discussed earlier, but formed into a closed loop, a perfect ring. The geometry of space-time around such a ring possesses truly interesting properties. If you were to traverse around this ring in a specific, precise manner, you could theoretically return to your starting point slightly earlier than you left. It would be a very minuscule effect, fractions of a second perhaps, but it would undeniably constitute a closed time-like curve. What is particularly elegant about the Roman ring is that it does not necessitate exotic matter or negative energy. It is purely a consequence of geometry, the natural curvature of space-time around a massive ring. Of course, creating a cosmic string ring would demand control over physics at energy scales comparable to the Big Bang itself, so it is hardly practical, but it demonstrates that time travel might not always require exotic ingredients. Sometimes just extreme conditions and precise arrangements of normal matter-energy might suffice. It compels me to wonder what other profound solutions to Einstein's equations we have yet to discover. The equations are notoriously difficult to solve in their full generality. Most known solutions are highly symmetric, simplified cases that render the mathematics tractable. But the universe in its glorious complexity is not perfectly symmetric. Real space-time is lumpy, irregular, brimming with stars, galaxies, and intricate structures. Perhaps within some of these irregular configurations, natural closed time-like curves or wormholes could form spontaneously under the right as yet unidentified conditions. Astronomers occasionally encounter cosmic objects that do not quite fit our prevailing models, anomalies in the data that take years to fully explain. Usually they turn out to be unusual but ultimately explicable phenomena, but occasionally they point to something entirely new. Pulsars, for instance, were initially mysterious, emitting regular radio signals that seemed almost artificial. They were eventually understood to be rapidly rotating neutron stars theoretically predicted, but not yet observed. Could there be similar surprises subtly hiding in the vast astronomical data, signatures of exotic space-time geometries that we haven't recognized because we simply don't yet know what to look for? The burgeoning field of gravitational wave astronomy has opened an entirely new window onto the universe. Observatories like LIGO and Virgo now detect ripples in space-time from violent cosmic events like colliding black holes and merging neutron stars. As these detectors become even more sensitive, they will undoubtedly observe more subtle phenomena. Could they detect the distinctive signatures of wormholes or time loops if they exist? Perhaps the gravitational wave signature would be unique, profoundly different from any known source. It is certainly worth looking, even if the chances appear vanishingly small. I am reminded of a profound quote from Arthur C. Clarke: "Any sufficiently advanced technology is indistinguishable from magic." Time travel would undoubtedly appear as magic to earlier generations and perhaps even to us. But it might not be magic. It might simply be engineering we don't yet know how to perform, physics we don't yet fully comprehend. The line between what is possible and what is impossible is not always clear, and it often shifts dramatically as our knowledge expands. You know, as we approach the culmination of this journey through the labyrinthine paradoxes and astonishing possibilities of time travel, I find myself contemplating what it all truly means for us here and now in this present moment. We have traversed wormholes and closed time-like curves, wrestled with the grandfather paradox, and the many worlds interpretation pondered the very nature of causality and consciousness. We have touched upon the profound insights of quantum mechanics and general relativity, the relentless march of thermodynamics and the grand cosmic sweep of cosmology. And through it all, there has been this persistent nagging question: can we transcend time, or are we forever bound to its linear, unyielding flow? Perhaps the definitive answer to that question doesn't matter as much as the very act of asking. The fact that we can even conceive of time travel, that we can employ the austere tools of mathematics and the profound insights of physics to explore its possibilities and its paradoxes, tells us something truly profound about human consciousness. We are not content with the world as it simply presents itself to us. We perpetually imagine alternatives. We probe boundaries. We endlessly ask, what if? This extraordinary capacity for imagination, for extending our minds far beyond immediate experience, is perhaps more remarkable, more miraculous than any time machine we might ever construct. When you truly ponder it, we are already time travelers in a very limited yet profound sense. In every fleeting moment, we move from past to future. We carry within us the indelible tapestry of memories of what was, and we meticulously craft plans for what might be. Our consciousness, in a way that inanimate objects cannot, intrinsically spans time. A rock exists only in the present moment, but you exist across time, intimately connected to your past selves through the intricate web of memory, and to your future selves through the subtle threads of anticipation. You are a temporally extended being, a four-dimensional structure, continuously moving through the space-time continuum, and we possess methods crude but undeniably real for influencing the future and preserving the past. We write, we record, we create artifacts that in their endurance outlast us. These are in essence messages to the future, a heartfelt attempt to reach across time and speak to people who do not yet exist. Every book, every photograph, every recorded song is a form of time travel, meticulously carrying information from the past into the future. When you immerse yourself in the words of Shakespeare or Homer, you're in that very act receiving thoughts from minds centuries dead, their wisdom preserved across time by marks on paper or pixels on a screen. We also preserve the past within the very cells of our bodies and the intricate wiring of our minds. Your DNA carries the genetic legacy of ancestors stretching back millions of years, billions, even to the very origin of life itself. The astonishing structure of your brain was meticulously shaped by eons of evolution, by the cumulative experiences of countless generations, perpetually solving problems and adapting to environments long vanished. You're in a very real and tangible sense a message from the deep past, a living continuation of patterns that have persisted through geological ages. Every heartbeat, every breath, every thought is an echo of that ancient pattern, meticulously evolved across vast stretches of time. The future too lives within us. Our present actions profoundly shape what will be. The choices we make ripple forward, influencing events long after we're gone. Scientists working today might enable breathtaking discoveries centuries hence. Artists create works that will move and inspire people not yet born. Teachers painstakingly shape minds that will in turn shape the future of the world. We cannot visit the future, but we are actively building it moment by moment, choice by choice. That too is a kind of power over time, modest perhaps, but undeniably real. I suppose what strikes me most profoundly about time travel paradoxes is how they relentlessly force us to confront the very structure of reality itself. Are we fundamentally free or eternally determined? Is the universe at its core fundamentally random or intricately ordered? Does consciousness play a special active role in the unfolding of physics? Or are we merely complex arrangements of particles obeying impersonal, indifferent laws? These are not merely abstract philosophical questions. They intimately affect how we understand ourselves, how we make decisions, how we ultimately find meaning in our fleeting existence. If time travel were truly possible, if you could genuinely visit your past self or witness your future, what would you say? What would you change? The question itself is almost painful, for it instantly reveals the regrets and the hopes we all carry within us. We wish we had made different choices, taken different paths. We wonder anxiously about outcomes not yet determined. This profound emotional weight we attach to time, to the past and to the future is an intrinsic part of what makes us human. We exist not merely in the present moment, but across time, perpetually haunted by what was and irresistibly drawn toward what might be. The paradoxes, the grandfather paradox, the bootstrap paradox, and all the others are not simply intellectual puzzles. They are at their core about identity and causation, about what fundamentally makes things the way they are. If you prevent your grandfather from meeting your grandmother, do you genuinely cease to exist? The question assumes a certain rigidity, a certain continuity of identity, that you are fundamentally the same immutable person across time. But perhaps that assumption is not quite right. Perhaps the you of today is already subtly different from the you of yesterday, connected by memory and physical continuity, but not absolutely identical. Perhaps identity is far more fluid, more dynamic than we typically imagine, and paradoxes arise precisely from treating it as rigid and unchanging. Some Buddhist philosophies, for instance, posit that the self is an illusion, that there is no persistent, unchanging essence that constitutes you across time. You're rather a continuous process, a dynamic pattern of change, not a static thing. If that profound insight is true, then time travel paradoxes become far less troubling, because there is no fixed immutable self to preserve or contradict. The pattern could loop or branch or tangle, and it would still be valid as a pattern still meaningful even without adhering to classical notions of identity. I am not asserting that this perspective is definitively correct, merely that different ways of conceiving identity and time inevitably lead to different intuitions about the nature of paradoxes. What physics has taught us again and again is that our deeply ingrained intuitions are not always reliable guides to the ultimate nature of reality. The universe is under no obligation to conform to the expectations of evolved primates on a small blue planet. We have had to relentlessly stretch our minds, develop entirely new mathematics, new conceptual frameworks to understand even a fraction of what lies out there, and we are likely still missing vast territories of understanding, grappling with phenomena we cannot even conceive of yet because we simply lack the necessary concepts. Time travel might be one of those profound things that requires concepts we have yet to develop, yet to name, or it might be far simpler than we currently imagine once we fully comprehend quantum gravity and the deepest, most fundamental structure of space-time. We will not know until we arrive there, until someone dares to formulate the right equations and rigorously test them against observation. That precisely is the enduring beauty of science. It surprises us. It takes us to places we never expected to go. I find something profoundly peaceful in the idea that all moments in time exist equally, that the block universe is indeed the true nature of reality. It implies that nothing is ever truly lost. The past still exists perfectly real, just at a different coordinate in space-time. Everyone who ever lived still exists vibrantly real in their moment, forever etched into the four-dimensional structure. And the future too already exists silently waiting for us to reach it. We are not in this view creating time as we go, but rather discovering it meticulously, revealing what already is. There is a timelessness to this picture, an eternal quality that is somehow deeply comforting. But perhaps it is not true. Perhaps only the present truly exists, and we genuinely create the future through our choices, through our free will. Perhaps time is an open, untamed frontier, and we are its pioneers, moving boldly into it, actively shaping it as we go. That perspective is empowering in a different, equally profound way, suggesting that our actions truly matter, that we are actively building reality rather than merely uncovering it. I do not know which picture is ultimately correct, or if either one fully captures the ineffable truth. Perhaps the question itself is ill-posed based on categories and concepts that do not cleanly map onto the true nature of reality. What I do know is that time is precious. We experience it, whatever its ultimate nature, as finite and irreplaceable. Each moment passes and does not return, or at least we cannot return to it. This creates a profound urgency, a poignant beauty. If we could revisit any moment infinitely, would moments matter as much? Would we truly treasure experiences if we could repeat them endlessly? Perhaps limitation itself is what imbues time with its value, what renders life meaningful. If we ever achieve time travel, I deeply hope we wield it wisely with profound reverence for causality and for history. I hope we do not treat the past as a mere playground to be altered on a whim, or the future as a resource to be selfishly exploited. Time, in all its cosmic mystery, deserves our deepest respect. We are undeniably creatures of time, shaped by it, defined by it in fundamental ways. To transcend it completely might be to lose something essential about what we are, but to understand it better, to probe its deepest secrets, to learn whether closed time-like curves are genuinely possible or irrevocably forbidden, whether many worlds truly branch or timelines remain fixed, whether consciousness plays an active role or is merely a passenger. These pursuits are noble, beautiful, and profoundly human. They relentlessly push us to the limits of imagination and mathematics. They force us to question assumptions we didn't even realize we were making. And in that magnificent process, we learn more deeply about ourselves, about how we think, what we value, what we fear. So thank you for joining me on this expansive journey through the paradoxes and the astonishing possibilities of time travel. We have covered an immense expanse of ground, from Einstein's elegant equations to the mind-bending realities of quantum entanglement from the theoretical tunnels of wormholes to the vast enigmatic stretches of cosmic strings, from the relentless march of thermodynamics to the very nature of consciousness itself. We have asked difficult, often unsettling questions and found that the answers are frequently more questions deeper and stranger than what we started with. That is the very essence of fundamental physics truly. Each answer, each moment of clarity invariably reveals new mysteries, new horizons to endlessly explore. As you drift off to sleep now, perhaps you can imagine yourself as a time traveller of sorts, moving gently through the night toward tomorrow. Your consciousness will pause, will go quiet for a while, and when it resumes, hours will have passed that you didn't consciously experience. Sleep is its own unique kind of time travel, a profound gap in awareness that carries you forward without the conscious journey. And in dreams, time itself often becomes fluid, elastic, sometimes flowing backward or looping or branching in ways that utterly defy normal causality. Perhaps dreams are the closest we come to experiencing non-linear time where past and future mix, where impossible things happen without evoking paradox. The dreaming mind does not worry about consistency or causation. It simply creates moment-by-moment experiences that do not obey waking logic. Perhaps that is worth contemplating as you gently fall asleep. This nightly journey into a realm where time truly works differently. Rest well, and know that the universe is vast and strange and full of wonders we are only just beginning to understand. Time travel may or may not be possible, but the fact that we can even ask the question, that we can explore it mathematically and philosophically, is itself a kind of miracle. Sleep now and perhaps tomorrow will bring new insights, new perspectives, new ways of thinking about these ancient profound questions about time and existence.